So last time we started with section 6.1, set of rational numbers. And we had gone through a few things. We had defined what rational numbers were, talked about what they're useful for, some diagrams, a little bit about the history of the development of where we've gotten to today and how we're using them, some different models, and simplifying. We had done some fun ways of checking to see how fractions are either greater than or less than or equal to one another. And then we're on this one, okay? So this is another example, much like actually the last two where we were actually comparing fractions, deciding which one's larger or smaller than the other one. And if you'll remember, we basically had, which one was it? 4 ways of thinking about this. One of them was actually a theorem that we had done where you cross multiply, basically. And then we can check whether things are equal or which one's larger. We had talked also about either reducing fractions or getting common denominators, either least common denominators or just common denominators. So those are the 4 ways that we had talked about doing that. And this example has the same kind of question. We want to know which one's bigger or smaller or if they're equal. So we have several ways to do that, and so we're just going to pick one and go with it as our first option. So which one would you like to try as our method for this first? Least common denominator. Why would that be so friendly on this particular one? You can see it. It's almost like right there glaring at you maybe, right? Okay, so one option here is to get a least common denominator, and I think that's a very good choice on this one. So what would you need to do to get a least common denominator on this one? Okay, so start which fraction? Okay, the right-hand fraction, and you want to multiply not just by 2, but by 2 over 2, actually, right? Okay, so our first fraction was 21 over 430. What would our second fraction be? 102 over 430. So which one's larger? The second one's larger, right? So the correct value of a symbol between them would be the less than symbol. The first one is less than the second one. There's a couple other things we can do. We're not going to go with all of those things, but I do want you to recognize that that theorem that we had before would also work fairly okay here. We had 21 over 430, and we sort of have this question mark in between. I don't have a symbol between there because we don't know what symbol goes between there, right? That's our goal, is to figure that out. And then we had 51 over 215. So one option is that we could, cross multiply, right? Let me use a different color here. So we could look at the diagonals here, and we could compare them. I don't want you to have to get out your calculators or anything, so let me just kind of tell you what the numbers are. It's 4515 on the top left to bottom right diagonal, and then the other diagonal is actually 21,930. So very clearly the second one is considerably larger than the first one. So you could do something with that pretty quickly. And this works really well, especially when you don't have the denominators are so very clearly one's double the other one, right? I mean, that was convenient here, but this would be a second option. Another thing to be aware of on this one is, to be honest, it's really easy to tell which one's bigger without even reducing or simplifying or anything. And so I want you to think about just for a moment, because we are going to talk more about estimation in some different sections here, about thinking about an estimation of what's going on here. If you think about this one, this is really basically like 20 over 400, right? Something like that. And this is about 50 over 200. And even without estimating in quite this way, we kind of think about it like that when we look at the numbers. The first fraction has a smaller numerator, which would usually indicate a smaller fraction, and it has a bigger denominator, which also indicates a smaller fraction. If your denominator is bigger, the fraction's smaller because you're dividing by something quite large. So on the on the first one rather, when we're dividing by 400, our denominator is about half of what it was before by comparison, and yet our numerator is almost twice as much. So it seems very obvious just by estimating and looking at the values that the value has to have this symbol right here between them, even with estimates going on. So you can also think about it that way, because this one didn't give you directions on how you had to approach the problem. So you have some choices. All right, a little bit of a different topic we didn't discuss last time is the idea about density, or the denseness of rational numbers. The denseness property of the rational number says the following. If you have two rational numbers, a over b and c over d, and they do have to be different, but if you have two rational numbers, there is another rational number between those two numbers. Okay? Now, let's just talk whole numbers for a minute, because they are rational numbers, but it's really easy to think about them in our mind. If you give me two whole numbers, 1 and 2, you know there's numbers between them, right? Well, that property is not special to whole numbers. It works for any rational numbers. Even if the rational numbers are quite close together, we always have the ability to do this. The easiest way to explain why this works is to think about visually what your calculator does when you look at a calculator graphing screen. Now, most of you probably experienced a calculator screen with graphs before, and most of the calculator graphs have the ability to be like zoomed in and zoomed out. Everybody so far with me? So one view of your calculator might actually put the numbers 1 and 2 kind of like spaced apart like this, and you can see there's space between them. But it might also be that you're looking at them and then you're looking at the 2 and you're looking at something that's very, very close to it, like 2.1. Right? That doesn't say 22.1. 2 and then 2.1. All right? Well, it looks like they're very, very close together. But if you move a cursor around, usually somewhere on the screen, you can zoom in and it sort of enlarges that view. Right? It makes it look like they're further apart than they were originally. So if we zoom in here, all of a sudden it looks like 2's here and 2.1 is here, and they look very far apart. This is the idea. The space that's in between them represents more rational numbers. And there's irrational ones too, but there are more rational numbers in between. And the easiest way to think about the reason that why that works in terms of like a decimal or a fraction is that you always have the ability, and this is one way to find, we're going to use another property here in a minute, but you always have the ability to find the halfway point, right? You just take the two numbers and you split the difference. That number, whatever you get, is another rational number. How do I know? Well, because if you take a rational number and you divide by 2, you get another rational number. It's easy to think about with fractions because whatever the fraction was, it just doubles the denominator. Right? That's what dividing by 2 does. It just increases the denominator by a factor of 2. So you always still end up with another rational number. Now, sometimes that's fine. I mean, you can find the rational number between them. One way to do that, and it's not a terribly difficult way to do that, is to simply add the two numbers together, right? So like add the a over b and the c over d together, and then divide by 2. Now, in fact, that finds the exact halfway point between them. You've probably seen that before. It was called the midpoint theorem when you did it in algebra. But you just add two numbers together, divide by 2. It's how you average something. That's how you average your grades. What's your exam average? Well, I only have 2 exams. We'll add them together and divide by 2, right? And that's fine, but if the fractions a over b and c over d don't have a common denominator, or they're really large denominators, or they end up with something very ugly, it just doesn't end up being very simple to do. You can do it, it's just not real clean. So we actually have another theorem that tells us how to find a number between them that's even easier. And this is a lot friendlier. At the outset, it might look similar to the other one, but it's actually quite better. So if we have the a over b and the c over d, and the c over d is larger, okay, then if you just add the numerators together, and you add the denominators together, you also get a fraction that's between the two. And that's a lot easier to do because a, b, c, and d are all whole numbers. So adding two whole numbers together is much easier than adding fractions together, right? So this is a very friendly theorem, actually. Nice, very nice to be able to use. And so we're going to do an example of this one next with two numbers that are actually very, very close together. So the first thing I'd kind of like for you to do is to take your calculator, and I'd like for you to put in 33 over 427, and then hit enter, and then put in 7 over 92 and hit enter. I just want you to look at the comparison in terms of a decimal and recognize these are close together numbers. They're not the same number, but they're awfully close together. So just key in both of them and take a look at their decimal expansion. You guys seeing what I mean? They're close together. But I tell you what, I do not want to add these two fractions together and divide by 2. 427 and 92. I mean, I don't want to try and find a least common denominator. I don't really want to multiply them together and get a common denominator. These are going to be large numbers. So I would like to avoid that if possible. And I can. I have the ability to do that using the last theorem. So again, look at what the last theorem says we need to do. We add our numerators together. We add our denominators together. And then we make a fraction out of those two values. So we're going to take these, and we're going to take the 33 plus the 7 over the 427 plus the 92. All right, 33 and 7, you guys know what that one is. That's 40. What is 427 and 92? 519. And then we would want to reduce if we could. We probably notice pretty quickly one's even, one's odd, so we're not going to be able to divide by 2. 40 also divides by 5. 519 won't, so we're kind of stuck at that point. I mean, 40 broken down is going to have factors of 2's, 2 and 4 and 8 and 5, and that's it. So we can't reduce this at all. This is simply the number between it. And if you want to verify it, you could take a look at the decimal expansion, right? You could make sure that, in fact, that decimal expansion is bigger than one of those numbers and smaller than the other one. So you could double check to make sure it makes sense to you. Any questions on that process? Okay, now I've actually already answered this question.
I have a question.
Yeah.
What were you saying about how you can check it with the numbers in between?
Yeah, you could actually write down a decimal expansion for the two numbers you started with, and then for this number that you just got, and make sure that the number that you got for your answers, decimal, was in between the other two. I don't want to talk about decimals too much because that's actually chapter 7, and we really aren't there yet, but I know you guys know some stuff about decimals, so if you wanted to visually check that, it's something you could check with. Yeah. All right, so I've actually already answered part B. So I want you to put down your answer in words, and we'll take a couple minutes here for you to write that. Why must there be a number between these fractions? In your own words. Why do you know that that has to happen? Okay. Okay, I see most of you have written something at this point. I'm not going to write anything, but I will repeat answers so that it catches, the answers on the video. What kind of things did you write down? There's lots of things you could have written down. So there's lots of possible answers. What did we get? Yes?
Because of Theorem 6.4, it states that if there's n fractions, there's a rational number between those fractions.
Okay, so we have a theorem that says that. Did anybody write down more about that theorem also? Did anybody cite that theorem or write more about that theorem?
I just said that in between two rational numbers, there's always going to be more numbers.
And that's actually what the theorem says in your words. Yes, you did. No, that's fine. That's fine. That's kind of what I was wondering, is if other people said the same thing without using the phrase by this theorem. So we have this idea about there being space, right? There being more space between things. Anybody else write some other things down? There's a couple other things that sometimes students will write down.
Fractions have infinite possibilities since the denominators can never equal 0.
Right. Well, and it isn't even so much that they can't equal 0, but they could equal anything, right, besides 0. Yeah, so we have lots of ability in our denominator to sort of subdivide things, right? So that's true, too. Very good. Anything else?
Because you can always divide the number by 2 or 5 or 6. It can be infinitely divided up.
Yeah, and that's kind of what I was talking about with the midpoint idea, right? We can always take two rational numbers and find their halfway point, the division by 2 ability. And that just creates another rational number in between. The exact rational number is the midpoint between the two. So any of those kinds of things are valid reasons to justify why we know that this is actually going to happen. Very good. Good job. All right, let's take a look at a student's work. Example 8, a student simplified the fraction m plus n over p plus n to m over p. So I've changed this a little bit from the last time I taught the class because I want us to think a little bit more in depth. Like I think the original question said, how would you help the student, which is kind of vague. Your book likes to do that a lot, actually. How would you help the student? I want us to think about some specific things that are going on in this situation. So the first thing I want us to think about is, what did the student do? Yeah, most of you are saying something about simplify or cancel. Those are the two phrases that are sort of in our minds of what's going on. Somehow they did something where they just did like, well, this is what they did, right? They just sort of ignored the plus n because it's in both pieces. Okay, so the first thing they did is they either canceled or simplified out in some way the plus n over the plus n part. Okay, so I do hope that you recognize that's not an okay operation. We'll talk about why in a minute just to verify it, and we'll do it very concretely. But first question I want to know is, why do you think the student might attempt to do that? Why would this be a reasonable thought that they would have?
It's the same on top and bottom.
There's the idea of it being the same on top and bottom, and you can do it with multiplication. So there is a place in which we can do this sort of, strike it out and ignore it kind of bit. But it isn't with addition. So they might be thinking about multiplication. The reason I asked the questions, or wanted to talk about the questions in this way, is because when you do see your book ask you things like, how would you help the student, or what would you say, I want you to think more concretely than you're right, you're wrong, and this is how it should be done, okay? It's much more helpful for the student to say, oh, I see what you did. It looks like you tried to do this, and that does work in this context. Validating that they're remembering something that actually is legit. I mean, it really does work, but it's not going to work here. So that instead of just striking them down, that they recognize that they've done something right. I mean, they do have a right process, just but with the wrong operation in this case. All right, so what would you then do to help the student? How can you show them that this isn't going to work, maybe? An example. Do you want to create one for me, Haley?
5 plus 3 and then 7 plus.
Okay, so we could create an example where we have something added to the top and the bottom. So if the student did have the ability to do this sort of canceling out, they would end up with 5 over 7, right? If their process worked, the answer should be 5 over 7. However, what is this answer supposed to actually be? It's 8 over 10, which also reduces, if you want to think about it, to 4 over 5. And then we can talk about how these two, or you could use the 8 over 10 instead of the 4 over 5, these two are not the same. And what are, again, some of the ways we could show they're not the same? A diagram would be a great way, especially if you've got visual learners. I absolutely love diagrams for young kids and for those who are just drawn to that visual imagery. How else could you do it?
Cross multiply.
Cross multiply. That's definitely an algebraic kind of approach, so this number sense idea. What else? There's at least a couple others. You could look at decimals if you've already talked about decimals. That's a good point. Didn't think of that one. But yep, you could. Yeah, you could get a common denominator in some form. Either least common denominators or simply just common denominators. So there's lots of ways to sort of justify in the end why these two fractions are not the same fraction, right? And depending on the diagrams, that sometimes the diagrams are exceedingly helpful, especially would be on cases where maybe one of the values that you're comparing is bigger than 1/2 and the other one's smaller than 1/2. That works really nicely. These ones might not work quite as nicely because of the numbers we've chosen, simply because it's hard to divide into 7 pieces sometimes, or also because both of these values are in fact bigger than 1/2. The visualness, if we're not being careful, might not work as well. So it kind of depends on the numbers you're working with as well. So all of these different things are things you can do to verify why these two fractions are not the same. And since they're not the same, his method of canceling out the plus 3's can't work in general. Okay? Does that make sense? Excellent. All right, this is an interesting problem I wanted to show you. And it sounds really wordy, but it's really not complicated. So let's read it together and take a look. If we take a set of numbers equivalent to 1/3, okay, so that just means fractions that are equal to 1/3, and we graph them as points on an xy axis, so that the numerator becomes the x-coordinate and the denominator becomes the y-coordinate. So all that's saying is that we're going to take the 1/3. The numerator is the first coordinate and the denominator is the second coordinate. So we have an ordered pair 1, 3. That's all it's saying. So, but if we do that with a whole bunch of fractions that are all equal to 1/3, The question is, what type of graph do we get? So the first thing we need to do is what?
Find other fractions.
Very good. We need some more fractions that are equivalent to 1 over 3. All right, so somebody give me 1, 2 over 6, 3 over 9. Okay, I don't want any bigger than that. Can we do something negative maybe?
-1 over -3.
Yeah. And if we wanted to, we could do -2 over -6 and so forth. This is sufficient for what we're going to do. So I'm going to stop creating fractions at this point. Usually to create a graph, we need at least 3 points, and now we have 4. So this will give us some kind of a picture of what's going on. All right, so I already have one ordered pair. It's 1, 3. What ordered pair comes from this 2 over 6? 2, 6. And 3 over 9? 3, 9. And -1 over -3? -1, -3. So our next step is to take these 4 points and to graph them. So I'm going to take a graph over here. I think that'll do it. I'm going to plot my points. All right, so I had the point 1, 3, which looks like it's about right there. Have the point, okay, my graph's a little bit off, isn't it? That's better. 1, 3, 2, 6, and 3, 9. And at the point -1, -3. And just as a reminder, this is my x-axis, this is my y-axis. That's what I was using on my 4 points. Is everybody's graph so far, the points look something like that? I think I got them all in there. Okay, so that's just 4 of my points. And I only wrote down just a few fractions. Is it appropriate to connect the points? Yeah, I mean, because all the values in between would also have that same 1 over 3 ratio that's going on. So we're going to connect the dots. It's not perfect, but it's pretty close. Now there's one, what kind of a graph am I getting? I mean, I did it. It's linear, it's a line. It has a positive slope, good. Now there's an error so far in what I've done though. Does anybody know what it is?
We went through 0.
What's wrong with 0?
It's not equal.
Yeah, 0 is a problem because the ordered pair at 0 would be, or at the origin, would be this. And does that have the ratio 1/3? It actually doesn't. So really in the middle we have an open circle. If you remember from an algebra class, an open circle means you can actually use that point in your graph. So we're going to describe it with a lot of the same language that you guys have already said. So it asks us in the question, what type of graph do we get? Well, you already said it's a linear graph. So it's linear with a positive slope. Do you know what the slope is? Can you tell? It's 3, yeah, because we went up 1 and over, or up 3 and over 1 with a positive 3 slope. But it excludes the origin. And again, because it doesn't have that ratio 1 over 3. So anytime we actually have fractions that are equivalent fractions, they would create, using this sort of a pattern setup, they would create a linear equation that would pass through the origin but exclude that point at the origin. It's kind of unique.